I'm sorry, I didn't record it, so I wanted to record it. So the speech that I was giving. So there are like three layers, right? So three layers. The outside layer, what is happening with the outside layer? The outside layer thickness, is it given? No. They just give you the emissivity value for the outside layer. Okay? Everybody notice that? So they didn't give you the thickness of the outside layer. That means you just have conduction for this two layer, which is the pipe and the insulation, calcium silicate and the steel pipe, right? Has got it so far? Alright. So why do they even bother putting that outside layer? They give you the emissivity, and the reason they put the emissivity here because they would like you to explore at the outside that both radiation and convection happen. Anytime you see emissivity, that clearly direct you to radiation. You remember that? All right. Now, if you're gonna do from the I would say homework number 2 background, right? If you're gonna do surface energy balance on the outside layer, right? So can you say the conduction heat transfer that is coming to the pipe and the insulation is equal to the radiation and convection? Can you say that? So we'll just bring that knowledge here, okay? Along with this chapter knowledge, which is obviously we have a cylindrical wall, which has two different materials, which has two different resistors. You just did the resistance equation, right? Everybody? What is the resistance equation? Ln of radius outside radius over inside radius divided by 2 pi kl. Everybody remember that? All right. So kind of getting a clue how to deal with this problem? No? Yes? All right. Let's do the problem then. Now here's one thing. It's a design problem. What is the safe to touch temperature for you? What temperature you can bear? You know the boiling temperature is 100 degrees Celsius. What is the steam temperature inside? 575, right? And you guys have seen steel pipe. Steel pipe is highly conductive, right? So if the steam is flowing through the steel pipe, the inside temperature of this steel pipe is 575. What is the outside temperature of this steel pipe? What do you think? In Fahrenheit? No, it isn't degree Celsius. If it's like inside steel is flowing through, why do that's another thing. I can discuss it later, but let's focus on this. 575 inside steel temperature. Okay, outside of the steel pipe. No insulation. Is it no insulation? Okay? Well, pretty close. That's the correct answer. Pretty good. I don't know. You don't know. I mean, but it could be very, very close to 575. It could be, I would say, like 574.99 or 9 or something like that. Very close because the heating steel is highly conductive, right? So I mean, the steel is not doing any favor to the steam, right? In terms of the temperature is still pretty much the same because it's highly conductive, right, people? So you are obviously putting in insulation, and the purpose of putting insulation, as like at the beginning we're saying, to keep the heat, okay, keep the heat inside, right? You mentioned that, right? But the other purpose is running on that steam, that steam running on the pipe in a power plant, possibly in a height like where it can be touchable, right? Anybody ever been in power plant before? No one. I was in power plant. I did my intern like 1 month in power plant. Okay, it is like very interesting things, and steam pipes are all over the places. Okay, all over the places. Okay, so crowded. You have no idea. All right, now this steel pipe carrying steam with 575 degrees Celsius. If you somehow touch on it, what is going to happen with it? It will going to burn immediately, and it's a serious burn. You're not touching boiling water. 575. So safety touch temperature is what? What could be safety touch? Must be less than 100 degrees Celsius for sure, right? Must be less than boiling temperature. Now, usually 50 degrees Celsius is the safety touch. Now, it's a design problem. You may argue, okay, I prefer 40 degrees. Now, the problem with the 40 degree is, what is the problem is, if you want to use the 40 degree outside temperature, design temperature, then the insulation will be that big. And you have to spend so much money. And there could be no point. Nobody normally touches steel pipe, right, with the insulation, and it's an accident that may happen. So even if it's a 50 degrees Celsius, maybe you are getting away with that without avoiding sue, right? You know what I'm saying? Okay. Bottom line, it's a design problem. I'm just trying to give you the background insights. A 50 degree something that you can assume. Okay, let's go to a standard way like dealing with this problem with the givens. Let's start with the givens first. So I want everybody to write the class note along with me. So it's a big problem, okay? So I want everybody to write the class note. Okay, no installation. Sorry, no exception. Okay. So whatever they gave you, I'm just trying to write the symbol for all of it first, and then I will start explaining, and I'm gonna give all the values. All right. Then H. All right. So they gave you all those values which I read through the problem before. So the inside pipe radius, they said they didn't give you the inside pipe radius. What did they give you? They gave you like the 300 millimeter pipe diameter. So if it's 300 millimeter diameter, what is the radius? 150? It's 150, right? Everybody want to take the class note. So if the thickness of the steel pipe is 30 millimeter, what would be the R2? 180, thank you. So you just add this 30 millimeter. And then this steel conductivity is given as 35 watt per meter Kelvin. The insulation conductivity is given as 0.1 watt per meter Kelvin. Take a look here. How many times is the conductivity? How many times is the conductivity for the steel compared to the insulation? How many times? 350 times. Do you understand what it means? So it's huge insulation happen in terms of the conductivity difference. That clearly tells you the emissivity value is given as 0.2, and this 575 degrees Celsius here, right? And then this T infinity out is given as 27 degrees Celsius. Now, they also give you another thing called T surrounding temperature. Why do you think they give you the T surrounding temperature? And by the way, this T surrounding is 27 degrees Celsius. Why do you think they gave you the T surrounding temperature? There is a radiation involved, right? The emissivity value is there, so there is a radiation involved. So this is another clue for you to deal with the radiation here. So the T surrounding is 27. Now, if there is a radiation involved, Logan, what do you want to do in terms of the temperature degree Celsius? Can you use the degree Celsius? No, you got to make it to Kelvin. So we're going to do the Kelvin here. So adding this to 73, we're going to give you 300 Kelvin. 300 Kelvin. And in case if you are wondering, 575 plus 273, which is 848 Kelvin, right? David, you are taking class note? You good? All right. Okay, so then H value is 6 watt per meter square Kelvin. And remember, I was saying the surface temperature outside should be less than 50 degrees Celsius. That is your safe to touch limit. That's the design problem. Now, this temperature can vary. And based on this temperature, everything else is going to change, like the insulation thickness and everything. Okay, so then the real thing is the sketch. So you do have this, let me do the sketch first. So you do have these multiple layers. So you have this steel pipe and the insulation, right? And then this is your pipe, right? Okay, and then you have this radius, right? This is R1. This is R2. Okay, and you have this R3. So question, what is the question? What you are trying to find here? Anyone? R3, find the R3, the insulation thickness. Okay, you see? All right, so this is what you want to try to find. And then these temperatures, okay? So like this is surface temperature here, the outside surface, right? And then say like this inside surface temperature, this TSI, right? And say like you have at outside this T infinity, right? And this H here. And say like inside temperature, there is the assumption that you'll be doing here. You see, the inside temperature is the same as the steam temperature, okay? That's the assumption. Everybody understand what is T infinity I? What is infinity means like the fluid temperature. I means inside, right? What is TSI? S means the surface. I means inside. So inside is still temperature, right? So yeah, that's how it is. So now let me draw the thermal circuit. So this is the bare minimum you want to do. Like when you're solving this kind of problem, you draw the sketch and then you draw the thermal circuit. When I'm saying thermal circuit, means it should have the resistance, it should have everything that we did in class just before, right? If you don't do that, that means the problem is incomplete. Okay, so you want to do it like this way. You want to put all the resistance. How many resistance here for solid here? We have two resistance, right? One for steel, another for insulation. Okay, and then at the surface of the insulation, how many resistance there? Two resistance, one for convection and one for radiation. Does everybody understand this? When we are dealing with the radiation, we are dealing with the surrounding temperature. When we are dealing with the convection, we are dealing with the infinity zero. By the way, those temperatures are same, but still you got to write it separately. And what is this temperature? You can say this is TSI. What is this temperature, guys? This node temperature? Anyone? TSO. Thank you. That one is TSO. Does everybody understand why it is TSO? How do you understand why it is TSO? Think about this. Say like this steel pipe. You have the insulation in the top of it, right? And then from the insulation, means from the outside of the insulation, you have two kinds of heat transfer happen. One is the convection, and another is the radiation, right? So you see, the convection one is the resistance that I draw that kind of going upward, and the temperature difference for that resistance is the outside air temperature and the outside surface. Does it make sense? That is TSO. S means surface, O means outside. Okay? The same thing is true for the radiation as well. Now you understand? Understand, right? Bring that home class note, right? Okay? Write the class note, okay? No exception. Write the class note. You bring the class note? A little bit faster. A little bit faster. Otherwise, I can't finish the problem. These are big problems. The big agenda that I'm trying to establish, okay? If you don't be fast, then it will be very difficult for me to finish. Okay, less amount of material I can finish. The class time is very limited. All right, so far you guys are good. So now this is my conduction, Q conduction. Now this is my convection, and this is my radiation. Now you guys remember the electrical sign, right? The Q or heat rate is equivalent to what? Current. So remember, in current, everybody understands current. Current is easy to understand, right? If a current passing through a wire and suddenly it gets divided by two wires, so that current must need to be divided by I1 and I2. Does it make sense? Okay, so if you have a Q conduction here to the solid, and that Q is the current, right? The total current, and it has two parts. One is the convection, another one is the radiation, right? So can I write this Q conduction equal to Q radiation plus, okay, Q convection? Easy to understand? So that is at the surface energy. That's the surface energy balance, right? At the outside surface. Just it good so far? All right. So find the insulation thickness and everything. Okay, let's do the assumptions. So the assumptions here. The steady state. What are the assumptions? What are the other assumptions? No energy generation. Can you assume 1D? Constant properties. All right. So now we're officially done up to this. Now the solution. Do you guys need some more time? All right, let's start. So we'll be doing energy balance. So this is, I'd like to write it in details. So energy balance or surface energy balance. Everyone's taking class note, right? How are you taking class note? Write everything, okay? At the outer surface of the insulation. Try to write a little faster. So you have this Q conduction equal, let me try to highlight that. So this is my Q conduction equal Q convection plus Q radiation, right? So Q radiation. Okay, so this is my equation number 1. I'm trying to do some color code so you can match. Okay, now can I rewrite this? So like everybody remember from last class that not last class, probably last week or something, I did write Q. What means Q single prime? Heat rate. Anybody? What means Q single prime? Heat per unit length. Thank you. Per unit length. Why do you bother with per unit length? Because the pipe length is given or not? Pipe length is not given. So that's why you do bother with the Q prime. You understand? Single prime. So can I rewrite this as like Q single prime conduction equal Q single prime convection plus Q single prime radiation. And I'd like to move this to equation number 1 instead of the first one. But you missed so many class notes, you have to probably watch the video lecture, okay? Yeah, it's a video. Harley, you are here. Take the class note. Okay. All right. It was good. Okay. So, okay. What is the difference between Q single prime and Q double prime? Anybody remember? Heat flux. Q double prime is heat flux. Is Q single prime is what? Again? Per unit length, right? Heat rate per unit length. All right. So now let's focus on that. See, this circuit has like 4 resistors, right? So this circuit has 4 resistors, right? So if you can just concentrate on the 2 conduction resistors only. Can I redraw that circuit with those 2 resistors and the temperature? Can you do that? Why? Do you know the TSO? Okay. Do you know the TSI? Okay. So what is unknown there? The Q. Does it make sense? So that is my goal. So let me draw it. Then you're gonna understand. So the conduction can be written as Matt, you understand why I'm doing it? So I have these 2 resistors, the solid resistance, the conduction sonar. Okay, so this is my steel and this is my insulation, right? You guys know what when I'm putting ST dot means steel, INS dot means insulation, right? It's a short form of doing that. And then what is this temperature? You guys remember like TSI and TSO, right? And what is this heat here flowing through this? Is it conduction? It's conduction, right? Through solids. So we have this conduction here. Okay, what are those 2 resistors? Let's see if we can write them, the conduction resistors. Let me write one of them. Okay, so ln of R2 over R1 divided by 2 pi K steel. 2 pi K steel what? What is that I'm missing here? L, right? Can you write the other one? The engine broke. It's more than 100. No, I'm good. I broke so many stylus pen over the years. It's more than 100. And I love to teach this way. I don't like to write it in code. So many reasons. Okay, so it is good. Whatever you know what you're doing now, right? So I'm gonna stand here for a minute. I'm gonna start working and I'm gonna see if you're able to write this resistance. If you are not, that means you're not following me. Okay, I'd like you to see you draw the circuit and you finish writing this resistance. Okay, that's what I want everybody to do. As I said, I'm gonna stop for a minute here. Okay, so you wanna draw the circuit and you want to finish that resistance equation. Okay, you see I have a line here. You should be filling out. So fill in the blank, numerator and denominator for the secondary distance. Okay, that's what you're doing. Obviously, you've got to draw everything that you're seeing here, right? It does. It does. Brother, you're well ahead. So now what do you do? This key conduction is missing. Can you find the key conduction? You're planning all the levels? Okay, Chelsea is way advanced. Okay, let's see. Logan, what you do? Now, can you write the key equation and find the key value, key conduction? Right, you need some time to understand. Therefore, you're not up to speed with the writing. Okay, what do you do now? You're gonna write. Oh, perfect. So can you write the Q conduction equation and find the value of the Q conduction? So you have some work to do, right? Okay, now can you write the Q conduction equation? Now you know these two temperatures, you know everything over here, right? Can you write the Q conduction equation and find the Q conduction value? Can you write the Q conduction equation and find Q conduction? Everything else is known except the L, right? But you know you are not trying to find Q conduction. You're trying to find Q single prime conduction in spiral unit, right? This L is going to go away. So we are actually trying to find this part and then point that equation number 1 and still you understand the reason I was saying to find the connection. It's actually what you're trying to do. You'll be one minute. Good. Alright. Okay, so everybody's up to speed. Make sure you go to write down faster, okay? And then that everybody's good. Okay, so let me write the Q conduction equation. So Q conduction TSO minus TSI divided by ln of, I gotta finish that. So ln of R3 R2 2 pi. Everybody please focus. Okay, all right, so ln of R2 over R1 and start taking the notes. So many to do, so many things to do. Okay, so the equation that I write, is it correct? No, what is wrong here? The L. I shouldn't put a L. Why? Because it's per unit length. The Q single prime. Do you see that? Why don't you write it? All of you, please. Focus on that. Now, I remember I was saying like and then I'm gonna put a Q single prime here. Okay. So remember that I was saying like, okay, find the Q conduction. Can you find the Q conduction? Is everything is known here, Harley? On the right side? Take a look. Do you know R1, R2? Do you know K, steel K insulation? Do you know pi? 22/7. You know the temperature? TSI, TSO? TSO you assume 50 degrees Celsius. TSI you know 575, right? So that means, can you find the Q conduction? No, Steve was claiming, Logan is claiming otherwise. What is missing? And is the R3 is what we are trying to find? The insulation thickness. So this is not solvable. But how are we going to solve it? Yeah, we've got to find the R3. That's the main thing. But how are we going to solve this R3? Take a look at that for equation number 1. In the left side, this is what we wrote. Can we write the right side? Convection and radiation. The equation for dome. So then we'll be doing equation number 1 and find that. That's what we're doing. Matt, you understand? Yeah. Okay, perfect. So then I'm gonna do this way. So you have this Q
convection single prime is equal. What is this Q convection single prime equal? Anybody remember? TSO minus T infinity, right? SO from outside surface, and 1 over what? H 2 pi R3. 2 pi R3 what? Do I need to put the L? If I'm going to put the L, hell, is it good? No, because I have Q prime, right? Thank you. So I'm not putting L. Everyone understand? So, and the radiation is, that's the trickiest one. What is the radiation? We know the radiation equation. We may not want to write it that way, but there is a radiation resistance as well. I'm not going to do it that way, and that will going to confuse you. So 2 pi R3 TSO to the power 4 T surrounding to the power 4. Can I write it? Radiation. Can I write this? You the convection is not right. What is missing here?
It's not, the temperature's not over, it's next to it.
Temperature is not over. Next to it.
Yeah, because it's HA times the change in temperature, not.
Oh, why do I write this way? I remember like this Q convection del T over R. Remember?
Yeah.
I'm writing the same thing in a little bit differently.
Oh, okay.
You understand?
Yeah.
I intentionally did it. Okay, if you want me to intentionally write the, I mean, because I'm writing everything this way, right?
Okay.
If you want me to intentionally write this, I said like I don't want to do the radiation. Yeah, I said I don't want to do the radiation. But if I'm going to intentionally write the radiation, then this would be looking like this: epsilon sigma 2 pi R3 multiply. No, I understand the radiation. I said like I'm not gonna write it, but let me put it, and you're gonna see how difficult it's gonna look like. So T surrounding square TSO plus T surrounding. You see, and that is your actually homework number 3. That what number 4 you are doing, right? First problem. That is the thing I'm asking. Okay. That's the first problem. Okay, do the derivation, find the radiation resistance. Okay. Anyway, so that's it. Then we're gonna do what? We are almost at the end of the problem. We'll just solve it. So we're gonna equation 1, right? We're gonna plug Q1 radiation, Q1 conduction. Sorry, Q prime convection. Okay, so then we're gonna have Q conduction. Everybody can write this equation now. All you gotta do is just solve it now. Q convection plus Q radiation, and then you're gonna start to write all those things that you did before. So for Q conduction, you have TSO minus TSI divided by ln of R2 over R1 divided by 2 pi K still plus ln of R3 over R2 divided by 2 pi K insulation equal. What is my Q convection? Now my Q convection is TSO minus T infinity divided by 1 over H 2 pi R3. Now the radiation, I don't want to write it in a complex way. I'm just simply writing to its usual form. Pi epsilon TSO to the power 4 T surrounding to the power 4, right? And then what? Then I'll just plug all the values, and I'm gonna solve an intrinsic equation where you have R3 in both sides. Okay, and they call trial and error. You guys ever did trial and error equation solution? Anybody heard about it? Trial and error. So trial and error means you just assume some value of R3. You're gonna plug it in both sides. If both sides is the same value, then your R3 value is correct. Obviously, your R3 value is not going to be correct at the first try, right? That's why you're trying. So you're trying and see how much of the error that you're getting. Means
means like the left side and right side, if it's not equal, that is error, right? So then you keep changing the R3 value until both values are same. That's called trial and error. But you can also get it like nowadays from using the solution application. Yeah, in MATLAB or Octave, you can do it. That in Excel also you can do it. I can teach you that at some point. But for now, let me just plug all the values and give the R3 value. So you have this 848 minus 323 Kelvin on the top, ln of 0.18 meter, 0.15 meter. Okay, just hang in there for a few more minutes. Okay. Yeah, if you have to go, it's in record. Please watch this. And if you have to go, have a very good break. Okay. If you don't have to go, just hang in here. If you have to go, watch the video lecture. Okay. Just 2 more minutes I need. Okay. If you don't have to go, just hang in here. Okay. So then I'll have this okay, 323 minus 300 Kelvin divided by 1/6 watt meter square Kelvin, and then 2 pi, R3 is not known, okay, plus 0.2, 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4. R3 is not known. This 323 to the power 4 minus 300 to the power 4 Kelvin to the power 4. That's it. Now you're going to do apply. So apply trial and error. And you're going to find the value. R3 is 0.394 meter, which is 394 millimeter. Okay. So the thickness, that's it. That's your answer. So thickness of the insulation, T insulation, is equal R3 minus R2, which would be 394 minus 180 millimeter, which would be 214 millimeter. Okay. So that's what we're trying to find. Now you can also find the Q conduction, right? I think you understand everything. All right. Watch the video lecture. Okay. At home, if you're missing anything, this problem is extensive problem. Very, very extensive problem. It requires for first time maybe more than an hour to understand. Okay. If you have any issue with understanding, let me know now. Okay. Rest is the math. Math you can do it by yourself. Okay. That's not a difficult part. Concept is so important. Right? Conceptually, question is if you understand it or not. Radiation, yeah, I kind of solved it here, you know. Radiation resistance. And in the book, they have the solution as well. Okay. This from the book. It's just encouraging you to read through the book. But the trial and error method could be a new thing for you guys. I'd like to show it to you when you're going to come back from the break as well. Okay. I'm not expecting you to know this, and we don't have time to do everything in one class as well. So I gotta do a balance. Okay? And there's exam is in week 9, day 1. Give a heads up. So this material will be there. Week 9, day 1 exam. Week 8, the new chapter is gonna be done. Done. Finished.
Is this week 7?
This is week 7.
Thank you.
Yeah, week 8 you're gonna come back.
Sounds good. Have a nice break.
Thank you. Did you understand? Steve, you got it? Is it exciting problem, Logan?
Yeah.
design problem. It's a complicated one, yeah.
Should I turn off the video? If you are done with the notes, you need some time? Okay, finish the note. I'd like to turn off the video.